Hello, I am Carlos Mastali. I'm assistant professor at Harvard University, and today I'm going to present our theory paper titled Inverse Dynamic MPC via Nullspace Resolution. Before explaining how we enable inverse dynamic MPC, I would like to spend time motivating why we need it. Inverse dynamic formulation helps to distribute the nonlinearities between the integrator and the system dynamic. This numerical strategy increases the algorithm convergence. Moreover, decoupling the system dynamic from the integrator reduces the numerical challenges in coarse optimization. Now the system dynamics and step integration are not tied. Last but not least, the computation of inverse dynamics and its derivatives are cheaper than for the forward dynamic case. You can find more details in the following reference. However, there are important challenges that prohibit us from developing inverse dynamic MPC. First, forward dynamic formulation fits naturally to traditional approaches for optimal control, such as DDP or FDDP. This is because we can easily embed the dynamics inside the integrator, avoiding handling equality constraint and reducing the number of decision variables when applying Gauss' principle of least constraint. Instead, inverse dynamic formulations require handling equality constraint and increasing the number of decision variables, as we can see in this equation. When handling inverse dynamic constraints, we need to include the generalized acceleration and the contact forces as decision variables as well. This increases the problem dimension. The way that we can address this challenge is by realizing that we can condense the inverse dynamics. Here, we describe the linearization of the inverse dynamic with bilateral contact constraints at the acceleration level. These are the first and second rows respectively. Now, if we assume that the inverse dynamics are feasible, then we can plot the expression for HID and condense this equation as you can see here. This means that our condensed inverse dynamic approach removes the joint torques as a decision variable and reduces the problem dimensionality. Another thing that we can observe is that optimizing with inverse dynamic constraint requires handling the system of equation and each node, or solving the system equation. It is worth noting that those equations come from applying the Newton method needed to compute the KKT point. If we apply the DDP approach, we can condense this system of equations and compute a control policy with respect to changes in the system state. We can further reduce this problem by realizing that a null-space control parameterization removes the Lagrangian of the inverse dynamic constraint. However, this is not a free lunch, as we need to perform an extra run rebuilding the composition, which is expensive in practice. The key observation that matters here is we can perform this decomposition and factorize the inverse dynamic problem, that's the second row, in parallel. This means we are actually reducing the algorithm complexity of the sequential recursive path, which is the main bottleneck. Our approach reduces the runtime cost always. It can reduce the computational cost by up to 50% with respect to a standard short complement factorization. This fact is key for enabling inverse dynamic MPC in robotics. In the bottom video, we can see that the short complement approach is not fast enough. This leads to locomotion instabilities on the animal robot, as we can see here. Now, we are also keen to follow the optimal policies generated by the inverse dynamic MPC and remove the need for whole body controllers. This requires mapping the inverse dynamic policy for the generalized acceleration and contact forces spaces to the joint torque space. We map these local policies in real time by decomposing the inverse dynamic function at the optimal values. Running these optimal policies allows the robot to handle instabilities or infeasibilities, and that's called from first principle. This strategy enhances the algorithm convergence of our MPC in real time, even when we push strongly the animal robot. Here we can see how our approach updates the feasibility of the kinematics and inverse dynamics when we push the animal robot in this experiment. Push recovers strategy leads to an instantaneous increment in the feasibility of the dynamics. Moreover, our feedback policy achieves highly accurate tracking of the angular momentum. Our inverse dynamic MPC pushes the limit of the animal robot. It enables animal B, a weaker version of animal, to climb stairs that miss a threat. This is an important capability that our method can enable many other robots. Another challenging task that our method enables is climbing boxes. Here, the animal robot can push its own kinematic and dynamic limits. Without doing this, the robot won't be able to climb this box. If you are interested in our work, please try our code open sourcing Crocodile. Thanks.